Okay, how's everybody today? Good, good, good. We're moving into the next lesson. We're going to talk about arc length and circular motion, which is comprised of linear and angular velocity, and we'll start talking about that in a lot more detail in just a few moments. Just a couple of reminders. We talked about the test this past Tuesday. I passed those back. When's the deadline? Okay, this coming Wednesday by 8:05 in the morning if you want to retake that. Progress reports are going to be submitted tomorrow. You'll be getting those next Thursday. So we're already halfway through the second 6 weeks. So it's not going to be long, before the second one's wrapped up. We're 2/3 done with the semester. But next week, I'm hoping we should be able to have this lesson wrapped up, everything taken care of by Monday. So my goal is Tuesday to introduce you to the unit circle, talk about patterns and how it's constructed, and then we can start really working on trig with respect to that. Okay, but in order to get there, we want to know this stuff first. So in geometry, we found if given a central angle and the length of a radius, we could set up a proportion to find the length of an arc in a circle. The arc length is a fraction of the total circumference, and the central angle is a fraction of a full rotation. So if we're looking at any 2 points on a circle, the distance between them, that's what we're referring to as arc length. Okay? And here we're going to talk about that as being S. So likewise, from geometry, we know that the ratio of the measures of the angles equals the ratio of the corresponding lengths of the arc subtended by these angles. So again, another mathematical definition that's not straight away very clear, but let's look at it this way. We were talking up here about taking the ratio of the angles, the revolution, and then the arc lengths and the circumference. So theta divided by theta sub 1 equals S divided by S sub 1. If we go ahead and replace theta sub 1 with 1 radian, and then S sub 1 with R as such, so that would be theta over 1 is equal to S over S sub 1 becomes R. We solve a proportion by cross multiplying, so 1 times S would tell me that S is equal to R theta. Here's my formula now for finding arc length. So again, you probably did it differently in geometry. There's many different ways. A proportion is probably the top way. But now that we know, or at least have a kind of an understanding about radians, okay, we have a different formula that's going to help me out with this. So S is my arc length, R is the measure of the radius, and theta is the angle measure. But really important, theta has to be in what? It has to be in radians, never degrees. So we're not talking about the mode of the calculator. As long as your angle is in radians, you are good to go. And I'm going to show you some in just a second here. In fact, let's go ahead and get right into it. Given a central angle of 60 degrees and a radius of 8 centimeters, find the length of the intercepted arc. Okay, so I got a circle here. Let me go ahead and kind of sketch what's going on. So we've got a radius of 8 centimeters and a central angle of 60. So let's say maybe right about here. This would be 60 degrees. So the arc length would be this distance, that portion of the circle. I want that. Okay, well, that seems pretty easy. All I got to do is multiply 8 by 60, right? And I'm done. 480. Has to be in radians, okay. It's really easy to forget. Always got to be in radians. So S is equal to R theta. So I'm going to take 60 degrees. What's the conversion to radians that we talked about? Pi over 180. There we go. Pi over 180. So if you'll remember, those degrees are going to cancel, and we're now in radians. In fact, 60 is the common factor. How many times will it go into 180? 3. So I'm looking at pi over 3 radians. Okay, so now I'm just going to plug into my formula. The arc length is going to be the radius 8 centimeters times the pi over 3 radians that we just got. Now, if we just multiply that, it's going to be 8 pi over 3 centimeters. But that really doesn't kind of give me a good idea of what the length actually is. Let me go ahead and take this off real quick. So I'm going to plug this in. So 8. Now, pi, I use this button down here at the bottom left. Okay, it's got a bunch of great symbols up here. 8 pi divided by 3. So let's say I want to round this to the nearest tenth. What should I be getting when I push enter? How many inches would the arc length be with a radius of 8 and a 60-degree angle? 8 pi divided by 3. Okay, so it's going to be real close to 8. So about 8.4, let's say. Okay, about 8.4 centimeters. Okay, so this distance here would be 8.4 centimeters. There we go. So hopefully you remember this from geometry. Now you probably did it a different way, but now we have a different formula. All right. So let's look at a couple of variations of this. Number 2, if a 100-degree arc of a circle has a length of 9 inches to the nearest inch, what is the radius of the circle? Okay, so we don't know what the radius is, but we do have a 100-degree central angle, and we're already given, let me do this in a different color. There we go. This distance right here is going to be 9 inches. Okay. So this time we're just working backwards, but we're going to go ahead and use the same formula. Does anybody want to come on up and show me how to do it? Okay. No volunteers. I do have my random number generator ready to go. 33. Fawaz. Thank you for volunteering. Okay, so to the nearest inch, I'm looking for that radius. Okay, so we have to convert degrees to radians. Okay. Okay, so 5 pi over 9 radians, perfect. Okay, so the arc length 9 equals the radian measure times the radius. Okay. So a couple things we could do. What are you going to make your next step? Okay. Oh. Well, there's just one thing wrong with it, but that's okay. So he's choosing to multiply through by a denominator of 9. Or are you trying to go straight to the radius? Okay, so 81 over 5 pi is equal to the radius. Okay, I agree with that. All right. Now, let me make sure that everybody's on the same page. What I just said, he's going to go ahead and multiply through by 9. 9 times 9 is where the 81 came from, but these 9s would cancel. Now, you could have done it another way. If you're dividing by a fraction, you would multiply by its reciprocal. So it still would have given you 81 over 5 pi. Okay, now this one says to the nearest inch. So let's go ahead and convert that. First off, is everybody okay with where we got that? Or does anybody want me to kind of elaborate? Gonna do elaborate a little? Okay. Let's say, instead of multiplying through by 9, okay, so I'll take this off right here. All right. Instead of dividing through, because if you have something multiplied by your unknown equals this value, you'd have to divide. But instead of dividing by a fraction, I can simply multiply both sides by the reciprocal. So those 9s would cancel, the 5 pi's would cancel. See, there's my radius, but now 9 over 1 times 9 over 5 pi is where we get the 81 over 5 pi. Okay, good. Let's see what that comes out to be. Control divide, so 81 over 5 pi. And what should I get when I push enter here? What was that? Okay. 5.2, okay, or 5.16, but it did say round it to the nearest inch, so I'll go ahead and say about 5 inches. Okay. There we go. Okay. Anybody having a hard time? Okay, pretty easy? Okay. That's the thing about those circle problems, they get around. Okay. Yeah. They get around. Yeah. By the time we're done, everything comes full circle. Okay. Okay, yeah, they're going about as well as they did in the previous classes. So. Okay, example 3. Find the angle in radians. Okay, then convert it to the nearest degree. So we have the radius. We have the arc length. We don't know what units in, so we'll just say 8 units. We're looking for theta. Okay, so S is equal to, bless you, R theta. So the arc length this time is 8 units is equal to the radius of 5 times theta. So what would theta be? 8/5, right? Now remember, the only way this formula is going to work is if theta is in radians. Since I was already provided the arc length and the radius, I have to believe that this is in radians. Okay. So we have 8/5 radians. Now we just want to go ahead and convert it to the nearest degree. All right, so radians to degrees. How do I do that? There you go. It was 180 over pi. So 8/5 times 180 over pi. Okay. So I'll just go ahead and multiply these out. So we have 8/5 times, let's get out there, parentheses, I'll put it in a fraction, 180 over pi. Okay. So what should I get when I convert it to degrees? Okay. 91.6. Now it does say to the nearest degree, so this one I'll say 92. Let's go ahead and say 92 degrees. There we go. And that's arc length. S is equal to R times theta. The only trick, make sure that theta is measured in what? Radians. That's all you got to make sure of. The rest of it's easy. Okay. Any questions on those? Okay, well now let's go ahead and start talking about linear and angular velocity. Okay, so have you ever thought about math while out for a bicycle ride? Sure, we all do. You know how to find your average speed by calculating distance traveled divided by the time from long ago. You remember your formula D equals RT, distance equals rate times time? Okay. I go back far enough. My teacher, when she first introduced it to me, called it the DIRT formula. Did any of your teachers do that? Okay, some did, some may not have. But in trig, we're going to call this linear velocity or linear speed. Okay, and rename our variables using v for velocity. So v is going to be how fast we're traveling, and s is still going to refer to the arc length. So linear velocity, if you have speed, okay, you're going in a specific direction, right? We're going to talk about vectors coming up in the second semester. But when we're talking about linear velocity, linear speed, this is how fast an object is traveling in a circular path. Okay? So you're still looking at speed, but it's in a circle. All right? So let's take a look at this example right here. Okay, and I've mentioned dimensional analysis before, and we're going to be doing it a lot with these type of problems. It says if you travel in a car at 65 miles per hour, how far did you go in 10 seconds? Now, we're only wanting the distance, right? We're only wanting the distance in miles. So something here has to drop out. What am I referring to? Okay, well, we got to do something to the hours, but time overall, I need to get rid of it. And see, that's our first obstacle. Our speed is in miles per hour, but we're wanting to know how far we've gone in 10 seconds. So my first step should be to what? Divide by 3,600. Okay, so Christian already has a really good idea of what we're going to do. Let me go ahead and make sure that everybody's on the same page. I'm going to start with my ratio. We've got 65 miles per hour, right? Now, we want to go ahead and convert this into miles per second. So this is where the dimensional analysis comes in. You probably have done this maybe in chemistry, maybe at some point. I've mentioned this before. Your teachers probably called this train tracks. Does that kind of sound familiar? Okay. Now, Christian automatically went straight to seconds, but I'm going to go ahead and write out every ratio because I want to make sure that everybody's on the same page. So what's between hours and seconds? Okay, minutes. So first I want to get miles per minute. So the hours have to cancel. So I'd have to put hours here, minutes here. So what values am I going to put in? 1 hour is 60 minutes, right? Okay. But now I'm going to go ahead and put in one more conversion to get the seconds that I want. So if I want minutes to drop out, I got to put those up top with the seconds below. And luckily it's the same ratio. 1 minute is 60 seconds. And see, this is what you're looking for. You're looking for these units of measurements to cancel. So see, those hours are gone. Those minutes are gone. So what I'm left with is miles per second. Okay. Now, what Christian said a little while ago was what somebody asked me already in first period. If we feel comfortable, can we just go ahead and say 1 hour divided by 3,600 seconds? If you feel comfortable enough with this that you can just go ahead and start combining your ratios, absolutely, please feel free to do that. Okay. If you need to go ahead and write it out, there's no problem there. So I just need to take 65 and divide it by that 3,600. So let's see what we got. 65 divided by 3,600. So I'm looking at about 0.018 miles per second. Okay. So now I can go ahead and figure out the distance that I've traveled. Because remember that original formula is distance is equal to r times t. We're just now going to change the distance to what? Like what's the arc length? S, and the speed is now v, right? We're just changing the variables, but the formula is going to remain the same. So I'm going to go ahead, in order to find the distance, I'm going to take this speed, 0.018 miles per second, and I'm going to multiply it by the time, 10 seconds. Now, you remember what I said at the start of the problem? Something has to drop out, right? Because we're only wanting the distance, which means we don't need the time. Yeah, so the seconds are going to cancel. So all I'm left with is miles. And this one's actually pretty easy. We don't need to go to the calculator because multiplying by 10, what's that going to do? Yeah, it's just going to move the decimal one over to the right. So about 0.18 miles. But this right here, when we're talking about linear and angular velocity, we're going to be doing this a lot in our problems. We're going to be converting units of time, units of measurement, and it could be anything. I mean, we could be talking about anything from as small as millimeters, all the way to miles. Okay. Any questions on that? Okay, well, let's go ahead and take a look at angular velocity. All right. Now, while we're riding our bicycle, think about how fast the wheels are rotating. This is what we call angular speed or angular velocity. So linear speed is actually how fast the object is moving, just what? In a circular path, right? Okay, so it's speed in a circle. But angular velocity is something different. The Greek letter omega, this curvy W right here, is the variable we go ahead and use for it. It's the accepted variable. This is the rate that measures changes in the wheel's central angle, theta, over time. So this is how fast it's rotating with respect to time. Linear velocity is the actual speed that the object is moving, but angular velocity is how fast it is rotating with respect to time. Okay, so the thing about angular velocity, it's always, 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 always going to be in radians per some unit of time. Could be seconds, could be minutes, could be hours, whatever it is you want it to be. Okay, because once it's in radians over time, once it's in radians, we can then associate that with a measure. You remember one of the things I mentioned in an earlier lesson was that we can't associate a unit of length with a degree. Remember, there's no such thing as degrees feet or degrees centimeters. That's why we have radians. Okay, so let's take a look at this problem. If a central angle spins 15 pi radians in 8 seconds, how fast is the angle spinning per second? Okay. Well, remember, angular velocity is always in radians per time, right? Well, what am I given here? I'm given radians and time. Okay, so if I want to know how fast it's spinning, the angle that is, okay, that would just be 15 pi, the number of radians, over the amount of time. All right, so that one was pretty easy to set up. Let's just figure out what that one is. 15 pi divided by 8 seconds. What should I be getting? Okay. Okay. There we go. So let's say about 5.9 Okay, radians per second. About 5. Oh no, actually this one running to the nearest thousandths. I'm sorry. So what was that? 890. 890 radians per second. There we go. Now remember, how many revolutions, or I should say radians, are there in one revolution? Remember, it's 2 pi, so 6.28, right? So this is very, very close to almost a full revolution every second. So it's spinning pretty quick. Okay. All right. A little bit of summary right here, a little more practice with some dimensional analysis, and we'll go ahead and get on to some actual word problems. I'll show you how this can really work. So linear velocity, remember that's represented by v. Okay, that's our variable. It has dimensions in length per unit of time. So it's length per time. So feet per second, miles per hour, meters per minute. The numerator units are measured in length. Okay, but angular velocity, we have this Greek letter omega, that curvy W. Always has the measures in radians per time, which I just talked about. So revolutions per minute, radians per second, even degrees can be used because that's still a measure of how fast the angle is changing. We can just simply change degrees to what? Radians. Yeah, we know the conversion, so that's pretty easy. Okay, the numerator units are angle measurements. So let's practice a few of these. A little more dimensional analysis. I want to take 60 revolutions per minute and first convert that to radians per minute. Okay, so I'm going to start with what I have, 60 revolutions in 1 minute. Okay. Now think about what we have here. We have revolutions per minute, but we want radians per minute. So what do we want to drop out? We want the revolutions to go. Okay, so let's think about how many radians are there in how many revolutions. Okay, what's that, Jack? Oh, that's in fact what you're going to get as a final answer. Okay, but the ratio, aren't there 2 pi radians in 1 revolution? Yeah. Okay. Yeah, so we want radians per minute, so I need to know what the conversion is. There's 2 pi radians in 1 revolution. So see, those revolutions now cancel like we saw the previous units cancel. And that's where he got the 120 pi. Good. So 120 pi radians per minute. And why don't we approximate this one as well? Why not? Okay, so what would this one be? Okay, so 376.99. So I would be really comfortable saying 377. So about 377 radians is per minute. Okay. All right. Now, in fact, when you're talking about linear and angular velocity, the only way to find linear velocity is you have to use angular velocity. And angular velocity has to be in radians. So this particular ratio is going to show up a lot when you're working these problems. Okay. Now, not on the next one, because what do we want? Degrees per second. All right. So it's going to be set up the same way, but you're going to be setting up, if you go ahead and do the full write out, it's going to be 3 ratios. So we start with our first one, 60 revolutions in 1 minute. Okay. So take a little bit of time. Let's see if we can all get the same answer. So I want to change revolutions per minute into degrees per second. Okay, is everybody about ready? Okay. So what do we want to go ahead and do first? Take care of the degrees or the seconds? Let's take care of the seconds. Okay, so what would be the next ratio? Oh, okay, so let's change it to seconds. Okay, so 1 minute over 60 seconds. Okay, so now we're in revolutions per second. We want radians per second, so I need one more ratio. Okay, so teach. Oh, not 2 pi. Because remember, we want what? We want degrees. Did I say radians? Sorry, I want degrees. We want degrees. Sorry. There you go. Think about the same ratio we had over here. We wanted radians per revolution, right? So 2 pi radians over 1 revolution. Well, here we're wanting to change it to degrees. So I'm going to go ahead and say 360 degrees in 1 revolution. Because in the previous problem, the revolutions canceled, and we want the same thing to happen here. So see, the revolutions cancel, the minutes cancel. So now I am in degrees per second. But do you also notice anything else? Yeah, this one was actually pretty nice to us. The 60s cancel as well. So 60 revolutions per minute would be 360 degrees per second. How many people got that one right? Okay, good. If you didn't get it right, what can I do? How can I help? Was it just time? Okay. Whoa, everybody's speaking at once. Okay. If you have a question, let me know. All right, so here's our summary with all the formulas. We can use the previous formulas to find a relationship between linear velocity, v, and angular velocity, omega. So this is the one that we're looking at right here. So v is my linear speed equals the radius times omega, the angular speed. Okay. Now the formulas are great, but I really just use this idea down here. Once you have the angular velocity, if you do one thing, you're going to have linear. So I look at it more like this. Okay. I'm going to go ahead and start with the number of revolutions with respect to time. All of these problems are going to give you that in some way or form. Okay, and you could be talking about anything out in the real world. I mean, you could be talking about a Ferris wheel that spins. You could be talking about a DVD. I mean, anything circular, right? So you're going to have a number of revolutions with respect to time. Now, we always like our angular speed to be in radians per time, right? So that's where that one fraction I told you about is going to play an important part. You'll always take the number of revolutions over time times 2 pi radians, okay, over 1 revolution. You'll always start the problems out like this. Because even if it doesn't ask for the angular speed, the only way you can get linear is by finding the angular speed first. So you're going to have to go ahead and set it up. All right, now this is omega. This is your angular. Or velocity, if you want to go ahead and do that. Now, once you have the angular speed in radians per time, what's the one thing you have to do and you now have linear speed? Just one little detail. Look at the formula. Aiden? What's that again? Multiply it by the radius. The second I take the angular speed and multiply it by the radius, that now becomes linear speed because now I have a unit of measurement here. So v is my linear speed. Okay. So all these problems are really going to be very, very similar to each other. Okay. If I take angular speed and multiply it by the radius, you will have linear speed. Okay. So why don't we go ahead and take a look at that first problem on the other paper? Because I think these notes are great, but I don't think it really goes into as much practice detail as we need for this one. Okay. And I've recently found out today that apparently vinyl records are making a comeback. So does anybody in here own some vinyl records? Really? And you have a turntable too?
Yeah.
I mean,
records.
wow. I mean, How long has that been a thing?
I thought you were going to call it. Yeah.
Oh, no, I'm actually genuinely answering a question. So, Jack. Oh, is there? Yeah, that's fine. I got to hand it to you. Okay. All right, so there's a little hand there. Okay, so let's take a look at number 1 here. It says a typical vinyl record has a diameter of 30 centimeters. When played on a turntable, the record spins at 33 1/3 revolutions per minute. Okay, here you have a circular object, and you're given the revolutions per minute. That's where we're always going to start. So in A, find the angular speed in radians per minute of a record as it plays. Okay, round to the nearest tenth. All right, so A, just like I mentioned a second ago, you're always going to start with the number of revolutions per time. Now, this won't be exact because, 1/3 is 0.3 repeating, but just for the sake of the problem, I'm going to say, okay, well, we have 33.3 revolutions in 1 minute. Okay, so we know how fast it's spinning with respect to time. Now, what's that one fraction that's always going to appear every time to change it to radians? Okay, 2 pi radians, okay, over 1 revolution. And every time you'll notice, your revolutions are going to cancel. So it wanted my angular speed in radians per minute, which is what we have here. So all we have to do is just multiply it out. Okay. So let's see, let me go ahead and get rid of this. So we have 33.3 times 2 pi. Okay, so what should I be getting? Okay, 209.2 radians per minute. Okay, good. 0.2 radians per minute. Perfect. Okay. Now, for B, find the linear speed at the outer edge of the record as it spins in centimeters per second. Okay, so one of the things we're going to have to change here is the what? There you go. We don't want minutes anymore. We want seconds. So this right here is my angular speed, right? If I want linear, all I have to do is what? Multiply by the radius. The second I multiply by the radius, I have linear speed. So for B here, I'm going to take the previous answer. So we have 209.2. That's my omega. Okay. Radians in 1 minute. Okay. Now I'm going to multiply this by, and here's what I like to do, because a lot of times, more than likely, you're going to have additional ratios with the dimensional analysis. So the radius, I just always go ahead and put it over 1. Okay, so what is the radius here? 15 centimeters. 15 centimeters over 1. Now we have to add on another ratio. And again, just like before, we want to go ahead and convert minutes to seconds. So I'm going to say 1 minute is equivalent to 60 seconds. Now see, here's the thing. As soon as you go ahead and multiply it by the radius, you have a unit of measure. Here we're measuring it in centimeters, right? So the radians just kind of goes away, because can we associate radians with a unit of measure? Yes. Yes. That's why we came up with radians in the first place. We can't do that with degrees. You can't associate degrees with a unit of measurement. So there's no such thing as degrees centimeters, degrees feet. But there are such a thing as radians associated with this. Okay, so let's see. My minutes are going to cancel. So I do end up with centimeters per second. I just have to multiply the 209.2 times 15 and then do what? Okay, so I'm going to multiply that by the radius, and then I'm going to divide by 60. Okay. So let's say to the nearest tenth, about 52.3 what? 52.3 centimeters per second. There we go. And this is linear and angular velocity. Okay. Any questions? Any problems? Okay, well, let's try the next one. Number 2. A bicycle messenger rides the bicycle shown. Now, it did get really close to your text, but what's the diameter of the wheel? 30. Again, so again, we have a radius this time of 15 inches. Okay. That'll help me out with part B. So during one delivery, the tires rotate at a rate of 140 revolutions per minute. Find the angular speed of the tire in radians per minute. Okay, so why don't you go ahead and take about a minute to do that. Let's round it to the nearest tenth. Okay, to the nearest tenth. So remember the setup. Okay, you always start with the same two fractions when you're dealing with angular speed or angular velocity. We still got a good 10 minutes, so we'll probably be able to finish up part B. No other class has gotten that far yet. Okay, so somebody help me play catch up to the rest of you. How would I start this? How would I find the angular velocity? Satish. Okay, so you always start with the revolutions per time. So we have 140 revolutions in 1 minute. Okay. And then I got to do something? There you go. We always want the angular velocity in radians per time. So here again, here's this common fraction, 2 pi radians in 1 revolution. Because the revolutions are going to cancel, we now have radians per minute. Okay, it's the same setup every time. Now, the only difference is, for the angular speed, maybe the unit of measurement is going to be different than what you're provided. We have 140 revolutions per minute, but maybe you're going to be asked, radians per second, radians per hour. So, you just want to be, mindful about that. So if you were to go ahead and approximate this, what do I get? How many radians per minute? I got 879.6 radians per minute. There we go. Perfect. All right. Now B, on part of the trip to the next delivery, the tire turns at a constant rate of 2.5 revolutions per second. Find the linear speed of the tire in miles per hour. All right, so at the very least, we can go ahead and set this one up. We'll probably go ahead and get the answer tomorrow. So we're going to start off, what are my revolutions per time? Okay, so it's 2.5 revolutions in 1 second, right? Okay. Now, if we're wanting the linear speed, I have to get the angular speed. So I need this in radians per time. So how do I do that? Again, what's that same fraction that's going to be appearing? The 2 pi radians in 1 revolution. Okay. So right now, if I multiply that together and stop, that is angular velocity. Okay. How do I go ahead and make it linear? All you got to do is multiply by the radius. In this case, the radius is 15 inches. So 15 inches over 1. I always put the radius over 1 because you're going to be dealing with a lot of fractions. So right now, the only thing that cancels are going to be the revolutions. Now, it's not that the radians cancel, but once we introduce a unit of measurement, they're no longer necessary. It's like they kind of drop out. So now I have inches per second. But we want what? Bless you. Miles per hour. Okay, so we'll just take it one at a time. Let's go ahead and start with the miles first. Okay, so again, I'm going to go ahead and write everything out because I want everybody on the same page. I'm going to have to go from inches to what? To feet, and then feet to miles. There we go. So what would be my next one if I want to go to feet? Okay, 1 foot is 12 inches. Okay. And now I want to convert feet to miles. How many feet are in a mile? 5,280. All right. So what would I put? 1 mile, 5,280 feet. Okay. So if I take a look at what I've done here, inches cancel, feet cancel. So now I've got miles per second. So now I got to focus on the time aspect. Okay. So we've already seen that. I want to go from seconds to minutes. So 60 seconds are in 1 minute. Okay. And then there are 60 minutes in 1 hour. So even though they're pretty far from each other, you still have a second above and below. So those cancel. The minutes cancel. So see, all I'm left with after all of this is miles per hour. Okay. So I would take 2.5 times 2 pi times 15 times 60 times 60, and then divide that by what? The product of 12 and 5,280. Okay, good. In fact, does anybody have that? I got 13.4. Yes, that's exactly what I got. Perfect. And that right there is dimensional analysis. That's linear and angular velocity. The other problems are going to be very, very similar. Is anybody having a hard time? Okay. So see, this is pretty cool, right? I mean, it's direct application to things you see out in the real world. So if you're driving along and you're looking at the speedometer and you see 30 miles per hour, you can go, oh, I wonder what that, you can kind of convert that. Or if you're on, did anybody go to the fair? Anybody go on the Ferris wheel? Okay. You could time yourself, how much time for one revolution. I mean, you could, math. Okay. I mean, who wouldn't do that, right? All right. Anyways, good.